Hello, I'm Sky, as Anand was saying. The general structure of the talk is going to be like this. I'm just going to give you a little bit of background as to why I'm here, who I am, what the project is. And then I'm going to talk a bit about the process of planning and executing a big formalization project, kind of how large projects differ from small ones and the kind of interesting things that you get out of that. So first, just a little background. So who am I? I am a PhD student in computer science at Nottingham, coming back to the maths department, which I graduated from last year. I've been working on a lean proof of ConNF since April of 2022. Now, I imagine most people here know what lean is, but I imagine most people here don't know what ConNF means. So I'll talk a very little bit about lean and I'll talk a bit more about ConNF. So the project is quite big. I've written for this project in total about 200,000 lines of code for it. This is what I mean when I say it's a big project. I should clarify, not all of those lines of code are currently in the project. That's including just all of additions and stuff. So this includes rewrites and everything. It's currently sitting around 26,000 lines of code, which is about the same size as MATLAB's entire combinatorics library for context. So the other interesting thing about this project is that before the formalization, there was no consensus that the proof that we formalized was even correct. We were working from a mathematical paper that was not published and had been in the works since 2010. And here's the context. So first of all, just a little bit about lean. So lean, obviously, as most of you know, I guess, who's used lean before? Presumably most of you. Okay, cool. I'll go through this quite quickly then. So lean is a programming language and interactive theorem prover. You can write programs in it. You can prove theorems in it. The underlying theory is based on the calculus of inductive constructions, which is the same kind of underlying theory as Koch and sort of like Agda and things like that. The consistency strength of lean is that of Z of C plus for each natural number n, concrete natural number n, there are n inaccessible cardinals. If you don't know what that means, completely ignore that. It's just if you want to know it and it's relevant for other things, then that's the information. MATLAB is big. MATLAB is the mathematical library that we use in Lean 3 and Lean 4 to do lots of proofs with. And it has everything under the sun from undergraduate maths pretty much now, and quite a lot of stuff beyond that. So this is the sort of stuff that's in MATLAB. And one of the reasons why we chose to do our project in Lean is because then we have access to all of this. And we don't need to write all of that ourselves. And so the MATLAB developers have, taken a lot of time and effort into making this a really, really good thing. So I'm now just going to talk a little bit about what ConNF is and explain what the actual project is. So ConNF and NF itself is about the axiomatic framework of maths that we kind of build up from. So most of maths nowadays is built on set theory. So the idea that you can boil every mathematical definition down to talking about some sets or collections of sets, which are also sets, and logical things and all of your normal operations you can do are just manipulations on those sets. But we need axioms for this set theory so that we make sure that we're not running into logical contradictions, such as the Russell paradox, Cantor's paradox, things like that. The usual axioms that we normally use for set theory are called ZFC, and they are hard. They are annoying to understand and annoying to read, and it's not very obvious what's actually happening. What's even worse is that the original developers of ZFC, so that is Samello, got it wrong. So the axiom scheme of replacement number 9 here was not included in the original versions of ZFC. It was actually originally called Z set theory or Samello set theory. It was just these first 8, roughly speaking. But then it was pointed out later by Frankel that Samello was secretly using this number 9. So the point is, it's hard to use axioms of set theory. It's quite hard to axiomatically work out what you're using and what you're not using. So how about we try and use a simpler set of axioms? That's what NF kind of is trying to solve. NF is a much simpler collection of axioms. It has 2 axiom schemes. The first one is extensionality, which says that 2 sets are the same if they have the same elements. This is just what it means to be a set. You're a set if you can be uniquely identified by what you've got inside. The other axiom is how to build sets, called comprehension, which says, given a formula that satisfies this technical condition of stratification, there is a set Y such that the elements of Y are precisely those sets that the formula is true for. So this seems like what we want in a set theory, ignoring this kind of annoying condition. This seems like, well, a set is just a collection of things that we can define with some formula, and 2 sets are the same if they have the same elements. So that seems like a good notion of set theory. The reason why this doesn't immediately break due to Russell's paradox and Cantor's paradox is just because the formulas involved aren't actually stratified. So, for example, you can't create the Russell class as a set because the formula X is not a member of X doesn't admit this stratification condition. I'm not going to talk much about NF because that's not really the focus of this talk. I just wanted to give you a little bit of an overview as to what NF was. So I guess, why do people not use it? Why have we stuck with ZFC with these complicated 10 axiom schemes when we could just be using something as simple as this? Well, there's lots of reasons, but the most important one for this talk is that logicians generally agreed that ZFC was consistent. So we say that a logical system is consistent if you can't prove any contradictions from it. It's quite easy to convince yourself, if you're kind of familiar with set theory and the way you can build stuff up, that ZFC shouldn't give you any contradictions. I say shouldn't, we can't actually prove consistency statements like this outright because of incompleteness and things like that, but essentially people understood that ZFC was consistent. The same could not be said about NF. The reason why is that in ZFC, you can sort of build up the universe gradually. You kind of build it up as a big old V where each initial segment can be constructed inside ZFC itself. In NF, because we have such sets as the universal set, which exists because the formula true is stratified, and so there's a set such that all of the elements are objects such that true, so we have a universal set. Because we have things like that, we can't really build the universe up bit by bit. So we didn't really know that NF was consistent. There's been a lot of attempted proofs of NF's consistency over the years, but in 2010, Randall Holmes claimed a proof that NF was consistent, which was incredibly messy. It works using this MacLane set theory with a tangled web of cardinals. It's this very Baroque sort of situation. Gradually over the years since, he's been cleaning up the proof, and in April 2022, a group of Part 2 and Part 3 students, including me, and including Yale sitting in the front row there, started formalizing his proof in Lean. And 2 years later, I completed the first draft of the Lean proof. So we now know definitively that NF is consistent because Randall's proof is correct, because we have this Lean formalization. The project isn't really over since then, though. I've been rewriting the code. I've been doing a lot of things to kind of clean it up. I'm still working on it today, and we want to release our paper soon, hopefully. Touch wood. There's wood on the floor. Okay, so just to briefly go over what the main idea of the proof is, and then we can get into the more Lean-based stuff. There's no obvious way to construct the NF universe recursively. This is what I was saying about how in ZFC you can kind of, you know how to construct initial segments of itself, because you can start building it up in layers. In NF, you can't do that. So instead, to show that NF is consistent, we're going to use the fact that NF is equiconsistent with TTT, or tangled type theory. Essentially, NF is like one big blob of sets, and in tangled type theory, you've got like a big old tube of sets that you're creating sort of in order on the way up. The point of this is that a model of TTT can be constructed in stages. So you have some ordinal indexing your stages. So this could be, for example, omega, which means your stages are indexed by natural numbers. And then at stage 0, your sets don't have any elements. And then at stage 1, your sets can have elements at level 0. And then at stage 2, sets can have elements at level 1 or at level 0. And so we can build it up piece by piece like this. Actually, even this is slightly too hard to talk about. What we're actually going to do is prove consistency of a finite axiomatization of TTT. This is just a finite collection of sentences that is equivalent to tangled type theory. So you can prove every theorem of tangled type theory using this finite collection of sentences. And just to show that we can, this is just for fun, I put all of the sentences on a slide. So what we've actually formally proven is that this collection of this goal is true. And I guess the important thing to point out is that there's nothing complicated going on. I'm not quantifying over formulas. I'm not saying anything about like meta mathematics. Really, everything here is very simple. I'm talking about universal quantification, existential quantification, logical connectives, elements of Kuratowski pairs. That's all that's going on. So the point is we've reduced our goal into this kind of simple form.
Are the superscripts sorts or something?
The superscripts are the sorts, yes. So the bit at the top, so each variable x marked with a superscript n is implicitly said to range over stage n plus n in the model. So you can think of these sentences as being instantiated at every level in the hierarchy. Actually, this is slightly wrong, I've just realized, but it doesn't matter, so we'll move on. Okay, This should say things about monotone functions from omega to omega. That's not important right now. Anyway, that's the kind of background out of the way. Now let's talk about the lean stuff. So a project like this is quite big. In April 2022, we started work as a summer research project in the SRIM program. So that the people working on it were me, Yael, who's sitting here, Patrick, Alexander, Angus, and Callum, and possibly a couple of others that I might have forgotten.
There were 6, so that should be.
There were 6, so
And
that is
Peter left if anyone then helped.
yes, I will talk about him in a bit.
Yeah.
But yeah, so these are all the students that helped out with it. So as a summer research project, it was supposed to take 8 weeks, but 2 minor difficulties with that. First of all, almost none of us had ever written a lean code before. And also, none of us understood the proof at all. So just 2 minor hurdles we needed to overcome. Well, first we needed to understand the paper. That's obviously the most important part. Papers are hard, and we had 8 weeks to do this. Also, the paper had lots of interconnected parts, which made it really hard to understand. Obviously, the problem is those interconnected parts are precisely why we need the lean formalization in the first place. The paper was interconnected in such a way that it made it difficult to review. It made it difficult to get published in a journal. It made it difficult to understand that you were actually reading a correct proof. That's why the lean formalization was so valuable for this project. But that's also why it made it really annoying and difficult for us to try and learn this whole thing in 8 weeks. Anyway, our solution to trying to understand this all and to try and get a handle on it was to make a blueprint. So who's used blueprints before in Lean? Not many of you. Okay, I will now regale at why blueprints are amazing and why you should use them all the time. So this, I'll just briefly explain what on earth you're looking at. This is a section of a big old dependency graph that was generated by Patrick Masso's brilliant dependency graph tool. What you essentially do is you have a copy of your paper that you're working from in LaTeX, and you just annotate it with little things to say, this is a lean definition, and its name is blah. This definition depends on this other definition. This theorem depends on this definition. The proof of this theorem depends on the proof of this other theorem, and things like that. And then it generates this brilliant graph that you can use to, for example, delegate work between multiple people working on a project at the same time. Or if you're working on it yourself, to feel like you're not overwhelmed by a massive amount of things left to do. Anyway, so what is a blueprint other than just a dependency graph? The idea is that it helps organize and visualize your definitions and theorems, and it helps work out kind of how you should do it, practically speaking. It's a version of the paper that's designed explicitly for the formalizers. So there may be, in general, a difference between the experts, the people who understand the proof, and the formalizers, which are the people who write that proof up in Lean. That was the case in our project, where we were definitely not the experts. We had no idea really what the proof said, but we were the ones tasked with writing it in Lean. Whereas the expert, Randall Holmes, didn't know anything about Lean, did know about formal theorem proving in general, but the idea was he would help to write the blueprint, and we would read the blueprint. The other good thing about a blueprint, obviously, is it generates this amazing dependency graph, which is very nice to look at. I already said this was written by Patrick Masso. And our blueprint originally was written by another academic working with us called Peter Lumsdain, who was absolutely brilliant and instrumental in the first 8 weeks of the project and helping us write this blueprint and letting us kind of work on it well. So I can even show you a little bit if we have time, but I'll skip over this for now. And then if we have time at the end, I'll come back and show you just what it looks like, because I think it looks cool. Okay, so we have blueprints and we have the original mathematical paper that you're working from. Why do you need both of them? What's the difference? So in blueprints, as opposed to papers, your internal dependencies have to be explicit. The idea is that if a theorem depends on some other theorem, you need to explicitly note that down in your LaTeX code, saying that this theorem depends on this other one. That draws a line on the dependency graph, and it makes it clear to the people who are reading this code, and as in the formalizers, in which order they should do things and how they should structure their code. Correspondingly, in mathematical papers, your internal dependencies are normally managed just using the flow of text. It's normally obvious if you're reading through and understanding everything, what things something depends on. But if you're a formalizer who only understands the small amount of the project that you're actually working on, it's not necessarily clear what dependencies a given theorem has. That's the kind of challenge with delegating such a big project.
Could I just
Yes.
point out that there are actually some complicated papers which have a dependency graph at the start.
Yes.
So
Yeah,
it's,
that
it's
is-
not like an entirely.
It's not a unique thing to blueprints, but it's a thing that's especially useful in blueprints, in my opinion. Yes, no, that's absolutely correct. Okay. Also in blueprints, your external dependency should point to precise theorem names. So correspondingly, in a human readable paper, you just have a citation or you'd reference someone else's work some other way. But in something like this, you really have to be explicit and say, you know, I'm talking about this particular invocation of Zorn's lemma that has these particular requirements, and really make sure that those hypotheses are really being met. It's very easy to, for a library author, for example, to not quite state the most general version of something, and you might not know that you need a more general version until later. So another thing about blueprints, human intuition is replaced with rigor. So this idea that in a human readable paper, the aim is to get the other person to understand what's going on. The same is not true of a blueprint in general. The goal is for the formalizers to be able to faithfully copy that into code, not necessarily to understand the whole thing. And often it's not necessary to understand the inner workings of everything. But what this means is that it requires a greater degree of explicitness. What I sometimes say is abstraction over analogy, which is generally often in human readable proofs, you have things like similarly to the proof of theorem 2.4, or it's direct from these facts, or you know, just copy the proof of this, but when you get to this step, instead do this manipulation. Those sorts of things are red flags in blueprints. It's normally more efficient to, when you're actually writing the code, it's normally better to work out an abstraction that lets you prove both of those things at once. I think that's all. So I'm going to talk a little bit about our actual blueprint and what we had to do to make our blueprint a little bit better, and how the blueprint differs from the paper version of the proof. So the first thing that we realized that we needed to change was the presentation of inductive hypotheses. So like I was saying, the proof is very interconnected, and this makes it difficult for a human reader, it makes it difficult for a computer. This is not like the fault of the person writing the proof, it's just a very interconnected proof, and it just is inherently a lot of that way. In the paper, these inductive hypotheses were spread out all the way throughout the paper in different sections, because that means that a reader isn't overwhelmed. And often you're proving an inductive hypothesis about the current stage straight after you assume it about previous stages. But because of the mechanism of the induction, you have to actually formally put them all in one place in order for the induction to actually go through. Anyway, I'll explain what I mean in a sec. The problem with this, obviously, with having all of these inductive hypotheses spread out, is that it can lead you to question whether this induction can work in the first place, because it's so difficult to describe and so kind of nebulous what's actually happening. So here's just a few examples. A hypothesis of the recursion. So, you know, we remark that this thing is true for this is a subset of this other set, which is now declared as a hypothesis of the recursion. So at some point in the paper, this was just like put in there. And the idea is that you then have to remember later to prove that about the current stage. There are other things such as, you know, we assume such things are present as a hypothesis of the recursion for beta less than alpha and construct them for alpha. So here alpha represents the current stage that we're building, and beta represents every stage prior to the one that we're currently building. And so note further a fact that we do not use directly, though it must be noticed. We're implicitly assuming that for all gamma less than beta, we're doing this thing. So these inductive hypotheses can be even more insidious. They can be implicit. You might not even be saying that you're using an inductive hypothesis, but it might be there. It then seems to be necessary to introduce the inductive hypothesis that's already been defined. This will follow from the eventually stated inductive hypotheses. And on the inductive hypothesis that there are these, we observe that there are these. I sound like I'm disparaging the paper. I really don't want to sound that way. This is genuinely clearer for a human reader in a lot of cases. The problem, obviously, is that in formalization, when you're actually writing this induction formally, you need to have this entire list of inductive hypotheses all at once right at the start. You need to make sure that they're all correct. So that's what we did in the blueprint. So here's a copy of the current bit of the blueprint. So we've now got a couple of definitions. So model data has got a specific set with a particular embedding and a group of permutations. a certain type class instance with a couple of technical conditions, and then this big old technical set of conditions. And this is the whole thing. The point is that this is all of it, and we know that this is all we're going to need. And through writing the blueprint, we found we needed to edit this list of inductive hypotheses gradually as we kept on working through it. But we eventually, finished writing the blueprint, and then we had a complete list of exactly what we needed. And this was really valuable in actually formalizing what we needed to do. Yes.
Is this for the entire proof, all of the inductive hypotheses, or like one section of the proof?
This is for the main induction. So this is the motive for the induction that lets us construct the next stage, given that we've constructed all previous stages. There are many more inductions.
Yeah.
Yeah, but they all are, all of the other inductions, but one, happen inside this one. So you need to assume all of these about all of your previous stages, and then do a bunch of inductions, and then you finally are able to prove all of these about your current stage.
Yeah.
It's a messy, this is what I was saying, it's a messy induction, and it's annoying to write down. That's why Randall chose to split apart the inductive hypotheses like that. Trust me, it's a sensible thing to do, but this is what I'm talking about. Blueprints are different to paper proofs in this way. Okay, does anyone have any more questions about this before I move on? Yes.
We were to also include that in the paper.
We are now doing that.
Okay.
That is now happening. Don't worry. That's now a thing. Although with slightly different notation. Like, I'm not talking about instances of type classes in the paper,
Sure.
but yeah, it's the same thing. So the next thing that we changed in the blueprint was we notice, of course, that there's a big difference between mathematical English and formal proofs. And I'm sure anyone who's used Lean is aware of this idea that there's a difference between what you write on the page and what you end up having to prove. And obviously, the more you're familiar with formal theorem proving, the better a blueprint you're able to write, the idea being that you write a blueprint in the knowledge that you're the one that's going to need to prove all of these things. And so you write this blueprint in such a way that your work, when you're actually formalizing, is hopefully as minimal as possible. And so that can obviously only really be done if you have a knowledge of how formal theorem proving works, whether like in the interactive mechanized sense or the more kind of traditional translate it into set theory sense. One of the common places where this arises is notationally complicated constructions. So things like, we can do this manipulation and it doesn't affect anything later, or things like, well, without loss of generality, we can assume blah. That might be true, and it might be convenient to a human reader to assume that, but that might not be the easiest way to write it in the code. It might be that we need more detail in order to write it in code. So just in general, we want in a blueprint to turn, we can do this into here's how to do this. That's sort of the motto, as it were. So here's some examples from the paper, not quite as many as last time. So here's an example of a proof. It just says, look at what happens to the position of the first element in an extension under the appropriate order as A inverse is applied repeatedly. Now, this might sound like weird, but trust me, in context, this actually makes sense. And it makes more sense than what I'm going to show you in a bit, which is what we put in the blueprint. The idea is that this is written for a human reader with the knowledge that you would know if you'd read the previous bit of the paper, that the position of the first element is some element of some well order. And so as you apply A inverse, this first element goes backwards in position. And so the idea behind this proof is that you're going backwards in this well order a certain amount of times. And because it's a well order, you can't go backwards more than finitely many times. And this is completely obvious to a human reader, but there needs to be details in order to put that into a blueprint. Then we can't just write this in Lean, right? We have to make details. So the question really is, do we want to do that when we're formalizing it in Lean, or do we want to do it in the blueprint? I'm kind of making the argument that you should do it in the blueprint because it's easier to refactor a blueprint that's wrong than it is to refactor Lean code that's wrong. And this happens more often than I'd maybe like to admit. So some other things, for example, this section is vitally important and should be ready to work on. Setting up the recursive definition may be nasty. Spoiler alert, it was very nasty. I'll talk more about this later. But the point is, so for the first one, this is the big junk that we turned this top bit into. And the second part about setting up this recursive definition and computation, we ended up stumbling upon these definitions and propositions. But the point is, we just did it all explicitly. and it meant that the lean formalization went a lot faster. Another example of things that are different in blueprints. We frequently realized that we needed to perform constructions at a particular stage. And we also needed to know that if we wanted to know about that construction at a later stage, we know that the construction didn't change. Oh, that sounds a bit abstract, but I'll give you some examples. Note that this definition does not really depend on the current stage alpha. It will give the same result at any stage of the construction beyond gamma and delta, which are lower stages. So the idea is we're doing this big construction and we might need to know some data. And the idea is we can construct it in the same way, just as long as we're past a certain point in the construction. And so this occurs all over the paper. So for example, it also should be clear that tau beta is defined in the same way at every stage with index at least beta. And it's important to notice this definition will be the same from stage beta onwards. And we define this, it should be evident that the definition given will give the same result at each stage greater than or equal to beta. And obviously this is great, and this is great for a human reader, but how on earth do you formalize being the same when the two things that are being the same have completely different types? Because one is depending on one set of inductive hypotheses, and one is depending on a different set of inductive hypotheses created later. Those different sets of inductive hypotheses are parameterized by a different type index, which filters through all the types. So now you have dependent type theory hell happening. And basically the point is this is annoying, and this is really difficult to deal with in type theory. It's sort of fine in set theory though. There's sort of two ways that you can go about solving this. Way one is to just axiomatize the behavior that we actually need, rather than just saying it's important to notice the definition will be the same. We can just request in the inductive hypothesis, adding more inductive hypotheses, this definition has this particular property, and that's all we need from it. That's obviously one way you can do it. Solution two is use a big abstract theorem. This is what we ended up making for running the main induction. So this says if you've got, roughly speaking, okay, I don't want to spend any real time on this because this is messy, but the point of this is that if you've got a bunch of inductive hypotheses with a bunch of properties that you've proven about how that inductive hypothesis relates to all the previous ones, and you can do this construction iteratively, then there are non-computable functions that execute that induction. So the point is you can either do this kind of axiomatization thing and work out the properties you need, or you have to appeal to some annoying induction things. Yes?
The type Q, type beta out there are the type universes of Lie.
Yes. Yes.
How much did you need to rely on universe polymorphism to formalize Quine?
The actual answer is not at all. We don't need universe polymorphism for anything. However, we do use universes for technical reasons. So
You need lots of universe bits.
no. The only real reason we use universes is in order to talk about cardinals in a more convenient way, because a lot of the proof revolves around cardinal arithmetic. And so it's easiest to define a cardinal by a particular quotient of the universe. Because Lean allows you to do universe polymorphism, the actual proof is parametric over a universe, but we instantiated at the end with universe 0, just to show that we could. Yes.
I think this is actually not the whole. You can't just say, oh, you only require one cardinal, because it's actually possible that you use bigger cardinals within the proof, but that won't show up in the types in the shard yet.
Yeah, that's
This
true.
is absolutely possible.
It is possible. But we make no essential use of it.
Yeah.
The proof runs in ZFC with no assumptions. So yes.
I can still add, however, that there is a tool that has been posted on Zolib by Mario Carnero to like instantiate all the results used in a specific proof. Yeah, like it just instantiates recursively all the universes to like the smallest possible interval.
Roughly it's n+4.
I think the maximum universe is it's 4. Yeah. So it's interesting. So it's interesting to notice this, because then you don't have to just believe Sky, you can check.
Yes. Yeah, you don't need to. Anyway, the point is we make no essential use of universe polymorphism. Sorry, does that answer your question?
Yeah.
Okay, so now that we have this amazing cool blueprint that's got all of these cool things, what can we do with it? So first of all, just a little bit of background about how the actual proof works. It takes place over 4 main stages. So first of all, we do the model construction. So this is basically saying, assume that you've built the model up to level beta, everything below level alpha. Then let's construct what's the stage at level alpha. What's the type of model elements at that level? What's our group of permutations that I was talking about? What's all of this other data? Then we've got to do the annoying job of proving that all of the inductive hypotheses are true. So to do that, we have another couple of stages, which involves freedom of action and the counting argument. Essentially, all this boils down to is a big, complicated proof that the inductive hypotheses hold. And then we can finish the induction, and we end up with a model of, hopefully, tangled type theory, which is what our goal was. Thanks to the blueprint, we managed to formalize all of phase 1, so the entire model construction, in just a few weeks. That was the first 4 or 5 weeks of the summer project. We did it, and it was very quick, and it was very efficient, and everyone was writing good code, and it was great. However, this was not the case for long. First of all, I'm going to go on a little bit of a tangent about why we can trust proofs made in Lean. And this will give you an idea as to what I'm then going to talk about is a big old mistake that I made somewhat about a year ago. And this is context for telling you my mistake. Yeah, anyway, so why can we trust theorems proven in Lean? Does anyone have an answer for that? Why can we trust theorems proven in Lean? Yes.
Because you have strong foundations, because of the type theory and a very small trusted code base, but not small.
Exactly. That's a great answer. That's pretty much what I wrote, but with more information. Yeah, the proofs it generates are compiled into a formal system that we know is correct, which is this kind of kernel language. And when I say we know is correct, I mean the kernel is small and we can check all of the code explicitly. That means that we can trust that whatever Lean has told us is correct is in fact correct. But how do we know that what Lean is telling us is correct is what we meant to say? There's a problem. We might have given Lean the wrong definitions. We might have told Lean incorrect things. And so it's telling us, yes, this thing is true, and maybe it is, but your definitions or your assumptions are just wrong. So here's just a fun example. Do you think that this is true or false in Lean with its normal definition of natural numbers? Not you, you know the answer. Anyone just want to say it? Just shout out a guess.
False. Please. To the power 0 might be 1. I don't know.
It is false because 0 to 0 is 1 in Lean. In fact, MATLib defines that in every ring, everything to the power of 0 is 1 always. So here's another fun example. What about n divided by 0 equals 0? Do you think that that's true or do you think that's false?
True.
That's true. But not only is it true, it's true by definition. This is a definitional equality of natural numbers. N divided by 0 is 0 is a definitional equality. It's induction on the right argument. Yes.
Did you check that recently?
Yes.
Really?
On Lean 4 online.
Lean 4 online.
Yeah.
Because I think
By
division is like
by intro semicolon REFL, it worked.
cool, because this is now well-founded recording, so we should not reuse.
Yeah, it should be.
Maybe okay. I was using Lean online, so maybe that's not the most up-to-date version of it.
It's the latest math.
It should be the latest monthly, but unless you
Okay.
was it on Lean Live?
Yeah.
Okay, then it should be.
Okay. Well,
Then
maybe
that's
I got that wrong.
Could it be that it first does the if it's 0 then thing else this and then the else bit is
Possibly,
well
yes,
under
yes.
recursion?
It's
Possible,
possible.
yeah.
It's possible.
Yeah.
Okay. Anyway, the point I'm trying to make is that Lean is very good at telling you when your proofs are wrong, but Lean is very bad at telling you when your definitions or your assumptions are wrong. This is obviously a major problem in formalizing mathematics because you don't know that what you've actually proven is what you wanted to set out to prove. So how do you solve this problem? Well, one way you can solve it is to try to translate non-theorems. So you can do things like prove that operator X does not in general commute with operator Y by just giving a counterexample. Things like, in the case n equals 2, this is just a simple version of this other statement. And these are sort of things that just help you be sure that the thing that you've proven is the thing you actually wanted to prove by linking it to other things that you're more confident on. And maybe a better way of doing this is just to state your results simply, using very few definitions. This obviously has relevance in some other Lean projects that people might have heard of. Does everyone know of Kevin Buzzard's project of Fermat's last theorem? Yeah, so Kevin Buzzard's been given some amount of money that's quite large to formalize Fermat's last theorem in lean. Over I think 4 years or something, 5 years. Okay, I'm not going to say how ambitious I think it is. But the point is, Fermat's last theorem is a really simple statement. It's just a statement about natural numbers, addition, exponentiation, and equality. And if you believe that lean has the correct definitions of those things, then even though you might not understand all of the stuff about elliptic curves, and you might not know that all of this complicated, I don't know, like sheaf stuff, whatever goes on in that proof happens. You might not understand all, well, I certainly don't understand all of that, but what I can be comfortable with is that if lean tells me this proof is correct, and the theorem statement that it's telling me is about natural numbers, and there haven't been any additional axioms introduced, then I can be confident that it is true.
Actually, that's not what Kevin has planned. I think he wants to formalize it up to the state of the art of the 1980s.
Oh,
So there
okay,
would
okay.
be a lot of complicated theorems still.
Okay.
Depends on.
But I think they will not be sorry. They will be like axiom,
Axiom something from the 1980s.
like, yeah, you know, right theorem and
Right.
axiom like
Okay.
construction whatever.
Okay, so yeah, minor correction, I guess, but I guess the general point is still that the idea is you want to state your results using few things, and that's kind of why, I mean, ages ago, I'm not going to go all the way back all that way, but when I had that big goal state on the slide, the point of putting it on that slide wasn't to actually show you it, it was to show that I could put it on the slide, and that everything about it was a really simple definition, and it has a meaning that's really self-contained, and doesn't rely on understanding 4 years of Galois theory in order to pass what the actual sentence means. Anyway, now I can talk about the big old mistake that I made and why I'm talking about this. So just a bit of context for why this happened, for the mistake, I guess. In the proof, we're recursively constructing these families of sets. So we have, our level 0 and our level 1 and level 2, and then we keep on going and we're constructing these stages of sets. Also at each level, we're constructing a group of permutations that acts on those sets. Now this is going to get slightly more technical. So each object that we're constructing has a combinatorial object called a support. This is just some small collection of things that sort of describe what parts of the model this object is allowed to touch. Supports aren't unique, but we can still use the axiom of choice to create a function that maps objects to a particular support for it. And that's totally fine. The characterizing equation of a support is this, which says that if you've got two permutations that map the supports to the same place, then it maps the object to the same place. This is the point of what a support is, right? What I mistakenly assumed, because I guess I just misread or misunderstood or something was lost in translation, was this. I assumed that you could commute pi outside this support function. And this is very, very false. You absolutely cannot do this. The annoying part of this is that I didn't know that I'd made this mistake until I'd finished stage 3 of the 4-stage proof. And I used this assumption in many, many places. And so this mistake was baked into the code in quite a serious way. And I thought the project was kind of over at that point, because I'd need to rewrite the entire code base. But I came up with a very silly workaround that I'll just quickly tell you about because it's very fun. The idea is that we'll just bundle objects together with a support, and we'll define that the action of a permutation on this bundled object and support just does it pointwise. And then the idea is that you can now just replace objects with these bundled things, where the definition of a support of this bundle is just its right projection. And then this equation is just true. And it's like, okay, yeah, this is obviously a really silly workaround. But the interesting thing about the fact that we're doing this in lean, and the fact that I have access to formal theorem proving, is that I could just plug it in. They satisfied all of the same inductive hypotheses. I looked at the list of inductive hypotheses, and all of them were satisfied. So now the induction just works on these instead of model elements, and everything's fine. And I didn't need to rewrite anything at all. And what's even better is that I ended up talking to Randall about this, who originally wrote the paper, and I commented about this mistake that I was making. And he said, actually, that's a really interesting idea. And then he started working on some things, and long story short, this mistake has made me a co-author of the proof because this idea of bundling things together greatly simplifies something right at the end of stage 3. So I guess what I'm trying to say is that proving stuff in Lean gives you some really nice consequences sometimes. Anyway, as if things weren't difficult enough, the proof now gets difficult. So just to remind you, the proof has 4 main stages. We've got the model construction, where we make a stage, given that we've made all the previous ones. Freedom of action, which I haven't said anything about. The counting argument, which is what I was talking about just there. So the counting argument was where I made that mistake. Finishing the induction, I kind of briefly touched upon with this big old mega type theory theorem. Our focus is now on a problem that we had during phase 2. There were some interesting problems and difficulties that we had with freedom of action that I want to talk to you about now. I mean, I need to give you a little bit more context. I promise this will be the last bit of technical stuff. But yeah, this will be worth it, I promise. So just to remind you, we're constructing this family of sets going up this hierarchy. In order to construct at each level, we need to know a size condition on all of the previous levels. We need to know that all of the previous levels had size equal to a particular cardinal called mu, which is set in stone at the start of the construction. So what that means is we have an obligation to prove when we construct each stage that the current stage has size mu. The problem is that that's stupidly hard because what we're essentially doing is tau alpha is sort of a modified power set of all of the things below it. And in general, power sets are size 2 to the things below it, not the size of the things below it. So we essentially need to show that this power set is very thin somehow. And that's hard. To do this, we're going to show this in 2 phases. First of all, we're going to show that there are less than mu descriptions of objects in each stage, and that's actually quite easy, where a description is some kind of combinatorial thing that just describes, sort of like a support does, but in a different way, kind of what parts of the model it brings together to create this set. And the hard part is showing that descriptions are sort of unique-ish. So only mu objects can have the same description. And do you agree that once we prove those things, we just say, well, there are less than mu descriptions, each of which have at most mu objects associated to it. So we've got mu objects in total. Is that all good? Now let's go even more complicated. So to prove this second part, we can't actually do this directly. What we can do is introduce that group of permutations that I talked about earlier. The point is, these permutations, the orbits of these permutations correspond exactly to descriptions of objects. So now we've got this second level of indirection where we're not talking about the sizes of tau alpha. We're not actually talking about really descriptions anymore, but we need to prove that these orbits correspond to descriptions and the orbits are only of size mu. So again, this is in 2 stages. We need to prove that the orbits have size at most mu, which is actually quite simple to do combinatorially. So the only thing that really remains is to show that if x and y model elements have the same description, then there's a permutation that sends one to another. So is everyone kind of following? That's kind of the end of the technical stuff. That's sort of the only context that we need. So the point is, for the long and short of it, is we need to know that if x and y have the same description, there's a permutation that sends one to the other. And that's precisely what the freedom of action theorem in the paper tells us, which is essentially any small partial definition of a permutation with no local contradictions can be extended to a permutation. The idea of this is that if you have 2 objects with the same description, you can talk about how those local bits map to each other. And freedom of action says that's enough. You can complete it to a permutation that permutes the entire universe. It sounds quite difficult, and it is. Freedom of action is a difficult proof, and it's essentially in the paper we were working from 2 pages of prose. This is the compact version. This doesn't have any of the definitions in that are needed to understand the proof. Also, this only details the construction of the permutation that we make, not the actual proof that the construction is correct. So from a formal verification standpoint, this is very different to a blueprint because there's lots of things missing, right? So we tried to make a blueprint for this in order to actually formalize it a little bit better, but it was just sort of too impenetrable. The proof just resisted what we like to call essential simplification. It resisted being split apart into lemmas and being proved piece by piece. It seemed like this massive induction. This, by the way, is another induction that's happening inside the main induction. And there's a second induction to prove the first induction was correct. But the point is that this is too impenetrable. There's too many things going on. It's difficult to split into lemmas. So progress kind of slowed because we didn't have a very good blueprint for this. Even worse, there was actually a minor mistake in the original version of the proof that we were working from. In order to do this, we have to do induction along a particular well-founded relation. It turned out that relation was not well-founded, in actual fact, very far from being well-founded, which is obviously a huge problem for actually doing induction, because you can only do induction along well-founded things. So essentially by August of 2022, progress basically stopped with this completely unfixable mistake baked into the code. It seemed like the project was dead. So that's the talk. No, so eventually in January of 2023, in January, I picked up the project again, and just after a gap of a few months, I fixed the mistake. This forced me to rewrite basically the entire project, to almost all of the code that we made up to that point. The fix was really easy, by the way. It was just very insidious. It just had fingers in a lot of pies, so to speak. Randall already knew about this fix. He'd known about it for ages. He's written many, many versions of this proof, and some of those versions had this weird extra bit in it, and some of them didn't. He thought it wasn't necessary, but it turns out it was. It's a thing that he was perfectly aware of, but just didn't think was relevant for this proof, and we proved by doing the formalization that it was necessary. Anyway, 100 commits later, in August of 2023, I eventually completed the proof of freedom of action. And then I now found myself in an interesting position of being basically the only person other than Randall that understands what the hell is going on in freedom of action. So I found myself spending the next year basically rewriting the proof. And so by a few months ago, so we're now like well into 2024, I stumbled upon a set of 14 simple self-contained lemmas. So that 2 pages of prose ended up being essentially, I'm skipping over definition numbers here, that's why these are not correct definition, like these are not in order, and there are gaps. The point is, all of these statements are short, and the proofs, believe me, are very, very short. Most of the proofs are incredibly direct just from definitions. There is no induction in any of these lemmas, which is very nice. The point of this essentially is that doing the formalization forced me to get better at maths and write a nicer proof. After doing this, I wrote a blueprint for freedom of action and formalized it in a day. I formalized all of this thing that took me 2 years-ish to work out in a single day, because we just had that much better of a blueprint and because I kind of understood what's going on a lot more. So that's kind of, again, I'm saying blueprints are really good and you should have a good one. Generally, Lean just encourages you to do things in a nice way, and it makes your life hell if you do things in a bad way. We found that was very true with freedom of action. When we were trying to formalize this, everything was very messy, and doing these results turned out to be a lot cleaner. Anyway, in the last kind of 10 minutes, I just want to briefly talk about, actually, does anyone have any questions about this just before we move on? Okay, cool. I'll move on to just the last little bit about the ecosystem of code. No code kind of stands alone. The code sits in a universe of other things, and this is true of any code, not just of formal theorem proving. One kind of big part of this is refactoring, of course. So at some point, we're going to need to refactor or maintain our code. This is obviously one big difference between small projects and big formalization projects, because in a small project, you might be fixed to one version of MathLib. You might, just do a result and then it's correct and it's correct and that's kind of fine. But that wasn't the case with Quine because it spans since 2022. A lot has changed in Lean since 2022. So yeah, one common cause for refactors is updates to external libraries, and this is true both in software development and in formal theorem proving more specifically. So I guess I'll just sort of say briefly how I manage this. So I try to synchronize with current MathLib about once every week, maybe 2 weeks if I'm not quite on the ball with it. Maybe it breaks something kind of once every month. Normally it takes less than 5 or so minutes to fix.
You're lucky.
Yeah, I don't depend on very much of MATLib.
Yeah.
The longer I wait before updating, of course, like the more inconvenient it gets. So when I had those like 3-month breaks of not really doing anything on the proof, that was difficult because most of the first week was just making it up to date with current MATLib. And I guess in the limit, as you wait more and more time before updating, you get the port to Lean 4. So as I'm not sure how many of you guys are aware, Lean has multiple versions. Lean has version 3 and it has version 4. This is sort of a Python 2, Python 3 situation, but worse in many ways. Essentially, Lean 3 works quite well, but Lean 4 is so much better. It has so many good things in it that you really want in a theorem prover and just a programming language in general. And so we want to transition to Lean 4. And more importantly, MATLib is now being developed in Lean 4. So if we want to depend on MATLib, we'd better do our code in Lean 4. So for this, we have the brilliant tool MathPort, written by Mario Canero, which translates Lean 3 projects into Lean 4. I think it's very surprising how well this thing works, given how complicated Lean as a programming language is. It's really quite good at translating code, and it was used to translate all of MATLib from Lean 3 into Lean 4. At that point in the project, because I was halfway through a rewrite, the project was about 10,000 lines of code, and it took just a week to port the whole thing from Lean 3 into Lean 4. Which, given that they are actually completely different programming languages, and the thing that we're doing is really complicated dependent type theory, that's, I think, really surprisingly short. So this just goes to show that, you know, communities are good, and your code is not kind of in a vacuum. It needs to bounce off other people's stuff. Even more things. So as I got better at writing Lean, I had to do less work whenever MATLib updated, even though the code base was larger. I guess the point that I'm trying to make with this is that as I got better at just writing Lean in general, I was writing better abstractions and things that depended on MATLib in more conventional ways and less kind of, I've only picked up the language 10 minutes ago sort of ways. The point is I was writing better abstractions, and so I was better at working out how to do this. Again, kind of the point of this is just your code doesn't exist in a vacuum, and you need to respond to the external pressures, and the better that you write code, the better it's going to be. And this is obviously nothing unique to formal theorem proving, but I think it's somewhat surprising that in a larger formalization project, it actually doesn't have maybe as much of an impact as I would have expected. Anyway, so what now? The proof is now complete. We know for a fact that NF is consistent. We know that Randall's proof works. We know that all of the parts of it are correct because I've translated them all into Lean. One of the other really cool things is that a lot of the abstractions that we made along the way, so things like the rewrites of freedom of action, they've made their way into the paper version of the proof. So it's a sort of dialogue between the experts and the formalizers in that way. So for example, that mistake that I made about confusing supports with things, that got turned into a very major modification to the paper that genuinely simplified quite a complicated proof near the end. And also the new proof of freedom of action is in the paper, which is very nice, and it's a lot more readable in my opinion. On the code side of things, I've written another blueprint because blueprints are really good, and I'm rewriting the code with it because the code was very messy, and I've still got kind of chunks of the bits of code that I wrote when I was still only a week old at using Lean. But now I know what I'm doing a bit better, and so I can write better code, and so that's why I'm really doing a rewrite. There's no mathematical reason to do this. The code is correct, but I just want to make it look nice and kind of more presentable to publish, right? The paper is still under development. We're still working on getting these abstractions to have nice paper forms as well as nice Lean forms. It's obviously a complicated process getting everything to match up. But yeah, we hope to publish our paper soon, and we hope to finish the project soon. But the point is it's done, sort of. Anyway, thank you. Okay.
So much for this great talk. Yeah,
Oh, thank you. Questions?
When are you actually proving con and f itself?
Okay, that depends on you, actually.
Yeah, that depends on me, I know.
So, as I was saying earlier, I prove a finite axiomatization of tangle type theory, which is 2 levels of indirection from NF. So, finite axiomatization to actual tangle type theory to new foundations itself. Both of those levels of indirection require substantial amounts of work, most of which should really be in MATLib. So, essentially, in order to prove ConNF itself, I'm sort of waiting on MATLAB developers to do things, or for me to become a MATLAB developer and do things. But I've got too much going on with the actual formalization of what I've got so far, so I'm not really heading in that direction just yet. Anyway, yes.
Substantial order of your current work, or like substantial something much smaller?
About on the order of the ConNF project as a whole, yeah. It's a lot of code. Essentially, we need to formalize all of multi-sorted logic.
Oh.
Yeah. Yeah, it's quite a lot. It's quite a lot. And we need to prove translation theorems between that and single sorted logic. And we need to prove a weird modification of Ramsey's theorem and some other thing, and Specker's proof, which is weird and syntactic, or there's a better version that Randall's made. So we can, the point is there's a lot of things that need to be done, and that kind of, the point of doing the lean formalization was to verify the complicated bits of Randall's proof. And I've done that now. The actual going from that to the consistency of NF proper is sort of, it's not the interesting part mathematically. So I'm not focusing on it.
Yeah, it's just like the history of maths I came before.
Exactly, yes. Okay, does anyone have any? Yes.
Going back to the freedom of action.
Yes.
Do you have a method somehow to come up with the simplification of the proof that you did? As in, were you going through the proof in lean and seeing sort of, oh, I'm using this here, and this comes up repeatedly, sort of taking out those lemmas and then seeing, oh, that's actually everything I need? Or was it sort of a different person?
That was definitely part of it. Having the lean formalization made me very aware of where I was using hypotheses, like you say. Most of it, I mean, admittedly, just came down to trying all of the things. Mm-hmm. And eventually something worked. Mm-hmm. I'm not really sure. The actual mechanics of the proof are not too different to the mechanics of the original proof. It's just phrased in, I think, a cleverer way. The idea really is that I came up with a better data structure that encapsulated the proof state. And so things that were previously inductive hypotheses are now functions on that data structure. So the idea is that the data structure holds less data than it did previously. So I need to prove less coherence theorems about it. And I can get back the original data by doing functions to it. So I guess that's sort of the point. I'm trying to minify my data structures. It's sort of like a code, I guess, a code refactoring thing. Mm-hmm. I guess that's sort of the main idea. Okay. Yes.
You mentioned you had the type theoretic result that was essentially implicit in the original proof, if I understand correctly.
Yes.
I suppose this could be used in other contexts, in another context as well. So.
Yes. Let me just find it. This thing. Is that what you're talking about?
Yes.
This is. I feel like this probably already has a name. It's probably already a thing. Essentially, I just realized we needed something like it and just sat down on lean and made it. It's not very deep. It's not very complicated. It's just really saying you can nest a couple of well-founded inductions inside each other and you get definitional equality in one argument, but you don't get anything in the other argument. It might be interesting to just kind of write this up on its own, but I don't think there's anything novel going on here. I think it's just just a way for me to write down, I am doing an induction in two variables in a type theory. But yeah, does that kind of answer your question, or are you sort of, okay, good.